Everyone, welcome to this webinar. My name is Johnny. I'm one of the founding partners at Marble, and I'm going to take a couple of minutes just to introduce Marble and a bit about what we do before passing it over to Nikisa to lead you through an exciting discussion about the cellulosic biofuels landscape and some of the exciting opportunities we're seeing in the space. So just a couple of words on Marble. We are a climate tech venture studio. So what that means is we partner with scientists, engineers, and operators, and we build new deep technology startups that are serving three purposes: either slashing emissions, removing carbon, or cooling the planet. At Marble, our thesis is on what we call hard climate problems. So this is anything that intersects with having a massive climate impact. We target a 1% impact at scale, meaning that it should have the ability to impact half a gigaton or more of emissions. We focus on companies that use new deep technology or deep science-based outcomes to achieve those things. And we go after venture scale outcomes, meaning that typically these are going after a huge market. We do a model where we look at researching areas. And one of those areas that we're going to talk to you about is the cellulosic biomass today. And we try to match the best talent with the best possible problem. If we find an interesting idea in the space, we then build a co-founding team, and ultimately we spin out that company and become the first investor, putting 250,000 euros in the new company. And for the cash, plus all the work we do in creating the company with you from scratch, we take around 20% of equity at pre-seed, and then help you with your next steps in financing and fundraising as you go. We were launched in September 2021, and we ourselves are backed by top climate tech investors across Europe and the US. We want to build 20 companies in this first vehicle, and we finished our first 6 today, who are all doing exceptionally well. We're going to talk about some of them in a minute, with 10 companies in progress and working towards that 20 company target by about mid-2026. So just to give you a flavor of the types of things we like to build, Airlium is working on reactive DAC, so integrating direct air capture and CO2 conversion into methanol, looking at decarbonizing things like shipping, aviation, and chemicals. Sention has a novel breakthrough approach to synthesize ammonia directly from air, water, and electricity without the need for hydrogen as a feedstock in order to decarbonize ammonia. Ammo Cooling is terraforming desert lands through the power of evaporative cooling. Vemma is unlocking geologic hydrogen, looking at producing green hydrogen, $1 a kilogram, almost anywhere in the world. Blue Mineral are pioneering a new carbon negative performance material for concrete. And we also have a stealth company now called Norma, who are pioneering the next generation of electrochemical direct air capture. So we like to go after hard problems where technological breakthroughs can have a massive climate impact at scale.
Thank you, Johnny, for the introduction, which goes really well with the theme of today, a very hard problem, which is unlocking cellulosic biofuels and potentially exploring it for Europeans' bioeconomy. So happy to take it over and have a lively discussion. During the presentation, I will stop a few times to go into the Q&A and answer some questions. And then at the end, there's always room to also discuss further. And if you have any other questions, you can always send me an email or react through LinkedIn. So let's try to keep this session very lively because it's very information dense. So you want to make a good balance of that for today. So the agenda for today is I'm going to briefly mention again why advanced biofuels are crucial for decarbonization, challenges in second-generation biorefineries that people have faced in the past, promising technologies, especially in pretreatment and fractionation, that I believe have come far away and are able to potentially bridge the gap and make advanced biofuels more compelling. And also Marble's focus on venture opportunities and maybe a call for action in that. So let's go into the first bits. So there's this motion that biomass is going to be quite critical to decarbonize where electrification is quite challenging. So as we've seen, shipping and aviation, for example, you cannot have a battery that is used for a long haul flight. You need very energy dense fuels. And because of that, electrification is not just going to cut it. The chemicals and petrochemical industry is also notoriously known as a hard-to-abate industry. So we need to find new ways to change the energy sources from fossil fuels in these industries specifically. And this will account to about 40 exajoules of energy consumption a year, with a CO2 emission of roughly 3 gigatons a year. Many people have speculated about e-fuels to be able to bridge this gap, and also biofuels. E-fuels, as you may have seen recently, has dealt with a lot of issues for its scaling up, because you need a source of biogenic CO2 or direct air capture with electricity and hydrogen. And the hydrogen economy hasn't arrived yet, and the costs are quite high still to be cost competitively with current fuels. So because of that, we want to look at biomass again, because we already have it previously, and I'll discuss the challenges later on with you, and see what are the opportunities that we could potentially valorize cellulosic ethanol and other biofuels for this process. Just to give you as a recap, we have a lot of biomass in the world. So if we account global agricultural residues from primary commodities, we can supply up to 45 exajoules of energy. This is a very optimistic scenario, and it's likely never going to happen. But what I want to show here is that for every bowl of rice, for example, you eat, you have the same amount of waste and sometimes even more. So the crop to residue ratios of most agricultural residues is extremely, there's just in general a lot of residues. So, and we don't utilize it enough. So this source is also it's also commonly known as a very underutilized source of waste that potentially could bridge the gap for our bioeconomy. Another important mention that I want to give is that according to the International Energy Association, by 2035, we have to massively increase the amount of liquid biofuels we need by roughly 150%. And especially what we see is that we need to move away from first generation biofuels, so specifically sugars and sugars and corn, and moving more towards more sustainable feedstocks that do not interfere with the human's food supply. Because of this, we see a big traction potentially in second generation biofuels to become to have a market entry point in this particular space. And then finally, I want to quickly highlight that especially the aviation sector is looking for solutions. There is a very big gap today for the supply of sustainable aviation fuels, and especially EU mandates are also further increasing the need and the market adaptation towards SAFs, because by 2030, 6% of SAF needs to be blended in with in aviation, and by 2050 it should be 70%. And importantly, what I wanted to highlight here is also that you have multiple processes to get towards sustainable aviation fuels, but there's still a very big range of uncertainty. Like I mentioned, the power to liquid, for example, hasn't been able to reach its targets that we want to. So there's going to be a massive demand. And I believe that biofuels is able to reach that. So I'm just going to quickly go into the chat to see if there are any questions already set. And then we can see from there. 1 second. Okay, so I have a question here that's why hasn't the industry embraced cellulitic microbes for biofuel production? That's a very good point. We're going to discuss that in a little bit. But I guess no more questions for now, so I'll just continue on with the presentation. So what are the challenges that we've seen in second generation biorefineries? So as you know, the second generation biorefineries is not a new concept. It's been here, and we've had a big wave between 2010 and 2015, where novel innovation has made it out of the lab and gotten towards pilot, demo, and even commercial scale. Let me walk you through the typical flow process of a biorefinery as a first step. So biomass, usually wheat straw, corn stover, sugar bagasse, are collected from ideally waste sources, and they are pre-treated usually using high temperatures as well as high acid contents. After the biomass is quite fluffy, enzymatic hydrolysis is continued. This is using either enzymes or a combination of enzymes and microbials that produce these lignocellulose degrading enzymes. In this process, sugar is produced. And then the final process, well, it's not the final, but it's a final for this flow, is that you produce ethanol from the sugars. And this is mainly the fermentative process that we all commonly know and is very well scaled up for example, in the beer industry. The main challenges, one of the big challenges in this process is in the pre-treatment as well as the enzymatic hydrolysis. The pre-treatments are, as I mentioned, at very high temperatures and uses a lot of high acid content acids that cause toxicity issues, as well as produce this thing called technical lignins. So this is a native lignin, and if you expose it to high temperatures and acids, it will become extremely recalcitrant. So sulfuric acid basically makes sure that the lignin is unutilizable. So that's why the valorization of lignin has been quite difficult in the previous years when acids are being used in a biorefinery. This is the same consensus why lignin is often considered a waste in the pulp and paper industry, because a recalcitrant molecule is inaccessible, so you cannot use it anymore. But lignin has many other values that it could offer. It is the most abundant aromatic chemical that we have in the world. So changing the way that we think about lignin and trying to fractionate it better could be a very interesting way to also have revenue from this stream specifically. A second challenge that we see is fermentation inhibitors. So again, when you have high temperatures and high acid content, you get production of furfuryls, which is this compound here, or even hydroxymethylfurfuryls, which is HMFs. Especially hemicellulose is hydrolyzed quite often with specific acids easily, and it produces these furfuryls. Furfuryls inhibit the downstream operations of the biorefinery, especially the enzymatic hydrolysis, as well as the fermentation step after, are heavily impacted. What happens here is that you not only have lower yields of sugar from the enzymatic hydrolysis step, but you also need to add more enzymes, which also adds costs because enzymes are not the cheapest thing in the world. So typically what we've seen is that fermentation inhibitors, not only fermentation inhibitors, but most biorefineries, when they went from a pilot to demo to a commercial plant, had a 50% decrease in ethanol yield, which make the unit economics extremely messy. Finally, I already highlighted that a little bit before, but enzymatic treatment is extremely slow and expensive. You're in a nightmare if your cost of good, so ethanol, is 57 cents per 57 cents per liter, but then only one step, which is the enzymatic pretreatment, could get to cost of almost 39 cents per liter. 68% of your product cost is just from the enzymatic step. And this doesn't even take into account that you need to pay for the feedstock. You have a distillation step. You have a whole capex that you need to amortize. It's just a recipe of disaster. And this is what people have seen often in the biorefinery space. So any way to decrease the amount of enzymes that you need for your process, as well as maybe bypassing enzymes completely, could be quite helpful. But there's a nuance there, because the reason enzymatic treatments became interesting is because they are also more environmentally friendly than, let's say, doing acid hydrolysis. So we need to understand this a little bit more and more granular to actually come up with the conclusions. But so it is by no means that a lot of second generation biorefineries have closed down when there was a very big push towards them in let's say 2010 towards 2015. The drives for these biorefineries, especially in the US, as you can see, all of them are in the US, was driven by mainly obviously the need for okay, US had corn ethanol already, and the Obama administration was heavily trying to get cellulosic ethanol also as a more sustainable source of ethanol into the market. However, in 2015, the tax deductions that you could get from cellulosic ethanol were stripped away because there were a lot of farmers' protests, especially in the corn belt. And with that being said, you cannot have a system that is still at a very early demo pilot become cost competitive with something like corn ethanol. And even the process, it goes from starch, which is way more easier to pre-treat and way more inexpensive than cellulosic ethanol specifically. Looking forward, there have been innovations that tried to learn from past mistakes and further innovate. So one of them is the sunliquid process, which is the name for Clariant's biorefinery that was operating in Romania So this process tried to innovate in multiple different ways. One of them is that they have an additional unit here, which is an enzyme production unit, which means that they were able to produce their enzymes on site. This was valuable because previous second generation biorefineries were reliant on the third party for the production of enzymes, which often caused delays, but also price fluctuations that increased the overall economics of the cost of the ethanol that they were able to produce. So by having this on-site production, they mitigated this challenge. In addition to that is that they did a chemical-free pretreatment, which had two value adds. One of them was that you have less fermentation inhibitors, so then the overall process efficiencies theoretically would be better. And also the wastewater is has less chemicals, which makes the capital investment in this unit to be also significantly less. And two additional things that was mentioned in the sunliquid process is that instead of only fermenting or hydrolyzing sugars, so C5s, they were also able to hydrolyze C6, so xyloses. And lastly, distillation step, the purification step is basically the distillation of ethanol into 99% ethanol. This is an extremely energy intensive and carbon intensive process. So they claimed they would also be able to reduce the energy cost by up to 50% through this process. In a similar note, there's this Prusa process that was innovated before by Beta Renewables, and then after it got acquired by another company, the name is coming in a little bit. This plant was located in Crescentino in Italy, and the few value propositions that they had was that the lignin that they were able to solubilize the lignin and use it as a steam and power. And he called himself an integrated energy production system. So the energy that you got here could fuel the entire plant. And they had feedstock flexibility. So they didn't only use wheat straw, but they also used corn stover and some dedicated energy crops in the region. And then finally, they took a lot of care about their wastewater specifically, so the effluent, by having a water and waste recycling unit, and thereby they were able to be called zero discharge. However, these innovations didn't deliver its potential either. So Clariant shut down its sunliquid bioethanol plant last year. They don't highlight completely what was the reasonings for the closure, but it was a combination of operational targets that were not reached, as well as additional investment required in the equipment of the system. And the Crescentino plant that was later acquired by Versailles dealt with a lot of feedstock impurities. So as you can see, the value add of having feedstock flexibility came back to become a problem, as well as high investment that needed for this zero discharge process. So apparently, I would have loved to go to the site, but apparently the site of the anaerobic wastewater treatment is almost the same size as the biorefinery plant in of itself. And then important is also to note that this plant was also hit by the bankruptcy of Mosici Sulfi Group, which was part of the which was part of the group that funded this process completely. This Crescentino plant is today still operating at lower operations than initially expected. So it is still there. So we have to see still how it will be in a few years. So I'm just going to stop here just a little bit just to see if there are any other questions that people have asked. I think there are quite a few that I saw, so let's just go through them. So I have a question from globally, biomass availability is not a major challenge. However, feedstock sourcing has and is expected to continue to be extremely challenging. How can companies navigate this? Absolutely. So indeed, the availability of biomass has not been an issue. It's usually the heterogeneity that makes it quite a challenge to operate with the right treatment facilities, with the right treatment methods. I have a few takes around that. First is that I think so I'm going to answer it later in the line, but I think having feedstocks, especially waste feedstocks, become a commodity could be a very good way to bridge this gap and have it on a tradable market, which allows for transportation as well as better quantification and understanding the quality of the feedstock in the process. But we'll discuss that a little bit more later. And then there was another question about how enzyme requirements to inhibitors in the biomass. Can you find a way to neutralize inhibitors? Yes, so this is also this is also something that people have experimented with the neutralization specifically. However, what you have is that during the hydrolysis, there is also production of these furfurols or other acids so you can neutralize it, but that can also destabilize the hydrolysis step that occurs itself. There was another question. Are there technologies which can process a broad range of lignocellulosic feedstock, or do you need to pick, say, wood chips versus, let's say, wheat straw? Interesting question. We cannot think of a biorefinery plant as an anaerobic digester. We can just put everything and then produce a specific output. I think because you want to have a biorefinery system that produces both high value and low value and mid value compounds in combination with each other, you need to have a process with a very specific input and refrain from using too many different types of feedstocks. Because of that, I think the motion of using dedicated energy crops with specific properties that are a bit more quantifiable could be a way to make the feedstock processing a bit more easier to come towards. So I'm going to quickly go through the presentation again, and then I'll come back with to the questions later on. But thank you for sending in your questions. Let's continue into the players in the second biorefinery space. So I mentioned a few that either closed or are still in halfway operating, but there are quite a few more that are existing. Some of them are using different processes as well as different feedstocks and are at a different stage and in a different location. So as this table nicely elucidates it, I want to quickly highlight 3 companies that I thought is interesting to mention in this webinar specifically. Blue Biofuels is one of them. As they last week, they announced that they opened a new plant that leverages they announced a new plant, a bioethanol refinery plant, which is something that we haven't seen in a long time. So that was quite exciting. So their goal was to produce 3 million liters of bioethanol, I believe, annually. And also important is to highlight newcomers in the space. So this year we've seen 2 companies aiming towards producing cellulosic biofuels come out of the laboratory. So one of them is Terragia. It's a US-based company that is at a pre-seed scale. They envision using thermophiles and bypassing completely enzyme addition into the enzymatic hydrolysis system. And similar with Celluol, which is a French-based company who has a similar value proposition for this. So it's interesting because we haven't seen many startups come over, and they both, with similar properties, came out of stealth this year. And these are also other projects and processes that we've seen come to life. So then you may ask yourself now, what makes an ideal biorefinery? So at Marble, we believe that it is combining the product, which, it's a combination of this feedstock, the process, and the product. And we'll go into all three of them for a little bit. So on a product note, as you know, lignin itself is the plant cell wall component that was seen as a waste. And if you're able to fractionate it at higher purity, you can make more use cases out of it. So we definitely think that lignin should be used as an aromatic chemical. But there are also other options, such as carbon fibers and also polymorphic foams for insulation of a house, for example. I found an interesting paper that showed that lignin could be used as a feedstock for cyclohexane derivatives. And cyclohexane, if you don't know what they are, they are these structures that have extremely high energy density properties. So going from a very a waste stream that is there's a problem and is incinerated towards a very high dense molecule is quite a revolution, and it's quite interesting to see if this is going to be something that we could work towards in the near future for lignin specifically. Okay. Then we also have the cellulose. So previously, people biorefineries only used the cellulose for bioethanol production. But we think that you can also, if you're able to separate it again and stabilize it well, you could also use it as for nanocellulose and also textile fibers. So having a nice combination of using the cellulose both for the bioethanol in a few operations, but also for additional more higher value products could be quite interesting to make the economics more interesting in the biorefinery itself. And finally, heavy cellulose. I remember the first conversation I had with someone about lignocellulosic biorefineries. They mentioned to me, hemicellulose, hydrolyzed first, done. We don't care about it anymore. But in fact, it is quite valuable to have it well solubilized or well separated, so you can have other valuable products be made out of it. An example is, for example, paint materials that people have used, that people are trialing now with hemicellulose specifically. Okay, and then from a process perspective, this is what one of the ones that I'm more excited about in the process. I believe that physical processes, although they've been exploited, I don't think we've cracked completely how we could use physical forces as much as possible to pre-treat the biomass and thereby decrease the amount of chemicals or biologicals or enzymes that you would need for the hydrolysis steps later on. So improvement in screw design and extrusion, I think, are going to be are quite interesting ways to deal with lignocellulosic biomass better. And it's not a physical process, but a maybe chemical process. I think supercritical fluids also offer quite a lot of interesting chemistries that we can explore to have better extraction and separation of all three plant cell wall components. In addition to that, from a chemistry point of view, there has long been a motion to do lignin first fractionation, which is to deal with the lignin first in the process and to ensure that technical lignins are not produced. Methods to do that that we've seen on a lab scale, but also on some demo skills are dial-assisted fractionation aldehyde assisted fractionation, in situ amination, as well as acid impregnation. Important is to know that not all of these processes are sustainable in the long term because you need to use intense solvents that could increase the amount of greenhouse gas emissions of the system. So you need to make a careful comparison between all of them. I personally am getting quite excited about deep eutectic solvents for this as a way to pre-treat biomasses better. From early experiments that I've seen recently, we've seen that they are quite recyclable and the cost of them are quite low, and the environmental burden is also not as high as some other solvents or chemicals like glycerol, for example, in the process. So quietly getting excited about this one. So would be curious to discuss this more with anyone who is interested on these solvents specifically. And then finally, biology is always evolving. And as we've seen also from the new companies that came to do cellulosic biofuels, what was true in 2015 may not be true 10 years later because we've gotten better at strain engineering and optimization. And we've also got better at this phenomenon of single-step saccharification and fermentation. This is the idea that initially what you would have is two reactors, one to do the enzymatic hydrolysis and the second one to do the fermentation. The hydrolysis typically works at 50 degrees, whilst the fermentation at 35 degrees. And they were used to be disconnected. And now the idea is that if you have very robust strains, they can withstand this temperature change, and you can do both then in one reactor, which decreases the capital cost of the entire biorefinery. So strain optimization is extremely important for this process, and novel thermophiles as well as other microbes are constantly being proved to show this efficacy and its efficacy essentially. And then maybe last thing that I want to say here is I'm not sure I truly believe in it, but I'm just going to mention it because I recently saw an article that wanted to recycle enzymes in the fermentation step better by doing ultrafiltration. Previously, this was deemed as too expensive to work, but I think there are some options that makes it a bit more viable potentially in the future. So I'd be excited to learn more and see more of this also in the future. And then finally, from a feedstock perspective, I think there are, as I mentioned before, I think availability of feedstock has never been the critical issue. It's connecting value chains with farmers and having deciding from a company perspective, if you're going to be located in a more urban area where the feedstock may be more expensive, or a more remote location where it may be cheap, but you don't have roads. I just want to quickly highlight again that in Europe, ag residues can support 7 exajoules of energy. This was from an analysis that was used between 2005 and 2015. UK was still part of the EU back then. And as you can see here, there is a lot of agriculture residues that we can use. And this paper specifically, they excluded all biomass that is today already being used for other processes, such as incineration. Well, not incineration, but with an actual use case, such as bedding, for example, for farms, etc. So I think there is enough biomass, but it's critically important that we can make sure that when there is a value chain, that is able to actually get you towards this feedstock. So any startup that is going to work towards that needs to have a very good model to be able to get as much feedstock. And with that, I finished. We are very excited, as you may see, for the potentials of biofuels for our economy. And we are excited especially to work with a talented scientist, engineer, operator, someone who has seen biorefineries go down and up and always thought, why didn't they do this? We'd be very happy to discuss this further with you. This is a QR code to look at the job description, as well as our website and our LinkedIn. So let's go into the questions. These webinars are a bit awkward because, I don't even know if there's someone still here. But here we go. Let's see what's happening. And thank you for putting up your questions. I'm going to go to a few of them, and then we can see from there. I'll go from the last one that was asked. So you mentioned thermophiles. Have you looked at hyperthermophiles? I think thermophiles are obviously have a very interesting membrane components that causes them to be extremely robust to many external factors. So any additional thermophiles is quite helpful to have. The important for them is that they are well cultivated, and if they are able to be cultivated and also be able to be engineered. Yeah, so that is what I would answer for now. I have a question from Xiao Wang. Yes, if you know of any other pilot scale second generation biorefinery that exist, please send them my way. I am well aware that I may be missing some of them. I try to capture as much as possible through this, but there may be a few that I'm missing. So thank you for sending this one. This is it's a fire renewable. Super cool. Thomas asked, we understand that most of these technologies have byproducts in their process. What is the average yield to the desired product? And how dependent are these processes on the sale of these byproducts to achieve competitiveness? Yeah, this is a very good question. So one of the people that I spoke to at TNO, which is a Dutch hub, they mentioned that 80% of the revenue of a biorefinery should come from 20% of the compounds, especially the high value compounds. So the economics are quite challenging, and you really need to rely on high value product production to have viability. So that is basically a small rule of thumb that I picked from someone that I spoke to around this. And here you can also already see the flaw. So if you have a very high value compound that only 3 people need, then yeah, you won't have a profit from this either. And this is also from a business model perspective, something that companies have dealt with previously in the past. So I hope that answered your question. If you have any follow-up, please let me know. So Henry asked, would the goal then be to develop a technology that act as an anaerobic digestion while providing high value products? So that's a great question. We always want something like an anaerobic digestion that can do this, but I don't think that is feasible. To think that we are able to do that, because if it was, I feel like people would have aimed towards doing this better. The truth is, feedstock heterogeneity is a big issue, and if you have multiple streams of feedstock use, your process is going to become less efficient than if it were to only use one source of feedstock. So I think that if you have a system that at a mid-scale uses one feedstock and can valorize it extremely well, I'd be more interested in that than the latter, which is having 3 to 4 feedstocks and having products that are not that interesting or not or yields that are extremely low. I think the first, so mid-scale, one feedstock, a very well production system has not been explored in biorefineries enough, and I'd be curious to see also how these innovations would play out in the future. Another question, do different fractions of final hydrocarbons allow to bridge cost gaps or selectivity is needed? So let me just read that again. Let me see. So I'm going to answer it the way I understood it, but please re-ask it if you think that I didn't answer correctly. So mm, 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 mm. So what I know is that let's say maybe I'll come back to the question in a little bit. I need to think about it. So on-site enzyme production is mentioned. What about in situ enzyme production within the fermenter with a cellulitic microbe? Indeed, this is an area of innovation that companies are exploring. So you produce the enzymes in site and don't even have a production facility for it. I think once we have more robust enzymes, more robust microbes that are able to do that, I think it's going to be quite good to have it in the system. But I do think that there are quite a few startups that are already exploring this in situ enzyme production in the fermenter instead of on-site production. Have you considered hydrothermal liquefaction as a pathway towards sustainable aviation fuels? So hydrothermal liquefaction is requires high pressures in the production system, and thereby I am a bit skeptical of its potential for SAFs. Well, not skeptical. I'm a bit cautious to think that that the pressure requirements can scale towards a very large project. Typically, what we are interested in is high yield fractionation, so you can produce multiple fuels and chemicals from the lignocellulosic biomass specifically. I have seen a company, I forgot the name, that are trying to do either thermal liquefaction. I think it's a very interesting technology. I think potentially we could use it very well for for more wet waste sources, so third generation biofuels, feedstocks, sorry. Have any company interested in valorizing lithium instead of using it as a heat source? Okay, so there are quite a few interactions here. Lithium indeed is one that valorizes lignin further. So yeah, definitely those exist. I don't see many other questions actually in the process. Let me just go down a little bit more and see here. What minimum level of expertise are you looking for in the FIR? So ideally someone who has a PhD or industry experience. Let's say you've worked in the pulp and paper industry, you understand all the pretreatments methods I mentioned, and even maybe know some others. And you're just creative. We are looking for people. We don't need a dilute acid, for example, to do it. Not that there's anything wrong with it, but we want to look at things that can really revolutionize this process by adding a component that increases yields significantly or changing it completely. So we want to really radicalize this process completely. I hope that answers the question. Given that connecting biomass producers to refiners seems to be so hard, isn't lignocellulosic fermentation as much a biomass brokerage issue as a lignocellulose conversion problem? Absolutely. I think it's a problem from both ends that we'd have to deal with. But till this day, the conversion methods have not been efficient enough to be able to basically valorize the biomass as much. So yeah, it's a double sorted question, but indeed, it's a good point. Sorry, I'm trying to read through the questions as well as see if there's still someone here. Here's a question from Samuel. When doing organosulf pretreatment to remove lignin, Are you worried about the solvent's residues inhibiting the enzymes? So yes. So Organosolv, I think there was a cleaning step that the people at the Fraunhofer Institute, as well as a startup that's aiming to commercialize organosolves, are trying to aim for it. So you can also recycle the process. So I think the inhibition of enzymes mainly came from the acid treatments that we've had. So I don't think Organosolv has that as its main challenge, as they're being quite direct in this process. Another question was, can on-site biorefinery help reduce cost? You need to produce on-site to have interesting unit economics. In most of these cases, if you have to transport the biomass from more than 100 kilometers, I think it's going to be unfeasible. So indeed, on-site is definitely necessary. Several second generation cell look at shut down. Yeah, so indeed, there have been many cellulosic ethanol projects that shut down, and they tried to switch this, and they don't target ethanol more. Important is to know that Europe doesn't have such an ethanol-heavy market because we didn't need to make a use case of ethanol before, like in the US. I think the alcohol to jet process for producing sustainable aviation fuels, because of that, is just significantly more mature in the US as it is in Europe specifically. But that's why a biorefinery approach is also quite helpful for this process. So you're not only relying on bioethanol, but also other important chemicals that you need to decarbonize. I think that's about it. I hope I didn't miss any question. Oh, here we have one. Benoit asked, do you have any review on price competitiveness of sustainable aviation fuel through advanced biofuels pathways? For example, ATJ versus HEFA versus power to liquid. Very good question. I had these numbers in my Notion, actually. HEFA today is the cheapest, well, not cheapest, it's the only form that SAFs are available today. Power to liquid is today seen almost 6 times more expensive than fossil aviation fuels. And then ATJ is about 2 to 3, but it's getting towards more cost competitive, but this is in the US. Please send me a message and I can send you some papers around this further, but it's a very good point to mention. I talked about deep eutectic solvents. What about biocompatibility and lignin structure? Is there any pilot plan based upon? No, there is no plant yet based on deep eutectic solvents. It is still in a laboratory scale, but literally 2 weeks ago, a paper came out that showed extremely high valorization of extremely high yields of the pretreatment of using these solvents, as well as its recyclability, because mainly the main issues with chemicals is that they are quite expensive, and if you're not able to recycle them, then the unit economics will not make sense, and deep eutectic solvents could be bridging that gap. So that's why I'm getting quite excited. Obviously, you know, things change when you go to a demo plant or a pilot or a demo plant in the process. But based off of these initial lab scale productions, I think there's a world. Yes, can you, I will send you the article around that after the webinar finishes. So someone mentioned without lignin valorization, second generation cellulosic ethanol will fail. But there, yeah, I may agree, but I think there's also, lignin is not the only place where you can get a higher value from the biomass itself. there are also some non-lignin derived high-value compounds that you can get from biomass. So indeed, you need to valorize the lignin, you need to fractionate it well so you can use it. But it's not only lignin that is going to make the cut for this process. And okay, I think I answered all the questions. So if no one has any more questions, please, please, we have a few more minutes, so happy to stay along here. I wish this part of the webinar was a bit more interactive because I don't know who's still here. But we are, I think, so I see some of the questions that are already answered, so I'm not sure if there were more. Oh, we have more from Tireth. Are SAF production from cellulosic biomass feasible by enzymatic routes? So the company Blue Biorenewables, based in the US, they are aiming towards making SAFs from using still some enzymatic processes, as well as some second-generation biorefineries exist today in Brazil that are aiming towards this. So it may be a feasible route. So we have to see that a bit further. And then maybe a final two questions. Co-solvent enhanced lignocellulosic fractionation. So I guess this is the notion of using two solvents in the process. Again, same things. If it's recyclable, then it's interesting. And if it doesn't have an effluent that is extremely toxic and you have to spend a lot of money to treat it, then it may be an interesting solution for fractionation. Okay, so with that being said, I think we are done here. Well, let's connect either on LinkedIn as well as on mail with with the Marble job description. And looking forward to see how we built this company at Marble, and maybe someone here will be part of that. So thank you very much.